Okay, class, so in this final video of Unit 3-2, we're going to cover pages 10 and 11. So first, let's start off by, I'll have you read this paragraph. Please do that on your own. But essentially, it's kind of a recap of what we saw. If the forcing term, or the right-hand side as I usually called it, was exponential, then the particular solution looked like an exponential of the same type, right? If the forcing term had sines and cosines, then the particular solution had sines and cosines of the same type, right? And finally, if the right-hand side had or was a polynomial of a certain degree, then the right-hand side was also a polynomial of that same degree, right? And so the only time we had to modify things is if our particular solution, if our initial guess at a particular solution was already represented in the complementary solution, then we had to multiply by a factor of t. But otherwise, that's pretty much how this is going to go. And so what I just said is captured kind of in this remark right here. Think of this linearly independent part right here. If a particular solution is not linearly independent of the complementary, that just means that part of it is already represented in the complementary, and so that's when you multiply by a factor of t. Okay, but let's look at the this table here. This gives us a few forms, common forms. So we've already seen before that if the right-hand side is a constant times e to the rt, then your first guess at a particular is, of course, a constant times e to the rt. No big shock there. Look back a few pages. You saw that if you had like a t squared or a t cubed, you started with a polynomial of that highest degree that's present, and then just count down, right? So like we saw when we had a t squared, we would have a t squared plus bt plus c. That's kind of what this means. Okay. Here, with sines and cosines, in both cases, you got a times cosine of that type and plus b times sine of that type. And even you could put here if f of t is actually a combo of these two. So let's say c cos at plus d sine at, right? That would also be a case that you would just use this right here. And we discovered that a few pages ago. Okay, so here's the new ones here. So firstly, if you have a constant times a power of t times e to the rt on the right-hand side of your differential equation, then, well, if the e to the rt weren't there, then it's not, then we're in the case 2 above here, right? And we see that it's not sufficient to just have a constant times that power of t. We had to count down all the way until we got to a constant, right? Well, that actually replicates itself here as well. So just because you have a constant times e to a certain power, times t to a certain power, like it's not sufficient to just have a constant times t to that power. You need the whole polynomial starting with that power and then counting down. And then now you just have that times e to the rt there that is necessary. Same deal here. You see with these two, of course, the e to the alpha t, cosine of beta t, and sine beta t, those should both be represented. I think that much is probably clear. It's just that because we have a t to a certain power, once again, we're going to use that to count down. So start with that power and then count down until the constant term as both coefficients of the e to the alpha sine beta t. And of course, you could put here, I'm not going to write it because I probably don't have enough room, but you could have if f of t looks like the sum of these two, so c times t to the m e to the alpha t cos beta t plus d t to the m e to the alpha t sine beta t, right? The form would also look like this as well. All right, so let's use this to help us with the next page. Okay, it seems like I have some kind of glitch on here, but you have the paper in front of you, so I think you should be able to do all of this, or to see all of this. First, what we're going to do is we're going to find the complementary solution. So the differential equation, which is conveniently not there, is 2y double, oh, there it is. Okay, of course it comes back. It's 2y double prime minus 8y prime plus 8y equals, and now f of t. So the complementary solution is, we're just going to pretend that there's a 0 here. So we get, for characteristic polynomial, 2r squared minus 8r plus 8 equals 0. We're going to factor out a 2, and then what we actually get is r minus 2 quantity squared. So please verify this, and we see that we get a solution of r equals 2 with multiplicity 2. Right? Okay, so that tells us that yc is c1 e to the 2t plus c2 t e to the 2t. All right, so nothing new there, I think. All right, so, well, here's our right-hand side now. So we're going to pretend the right-hand side looks like e to the 2t cos t. Well, looking up at our table, in this case, m is 0, and so it's just, it'll be e to the 2t cos t, right? But now since m is 0, we just get a constant term. So I think our yp guess is going to look like a e to the 2t cos t. And now, don't forget, we need to add e to the 2, b to e to the 2t sine t. Right? And now you have to ask yourself, is this represented, is any part of this represented in the complementary? And the answer is no, right? These are e to the 2t's without any sines or cosines, and so those are sort of separate from the ones with sines and cosines. So that's it, right? Coming down here, our guess for yp, well, this is a linear polynomial, so we should have a guess of a linear polynomial, at plus b. And now you ask, is a constant times t represented over here? No, right? There is a constant times t, but it's multiplied by the e to the 2t, and those two things are not the same. Similarly here, is a constant just in the complementary? And the answer is no, right? We don't have just any plain old constants over here. So that's it. All right, now, here's where things get a little bit interesting. Our guess is going to be, it's at the very top of that chart, I think, a e to the 2t. But now you see that a e to the 2t is represented right here, right? A constant times e to the 2t. So I need to hit it with a factor of t. But now you go back and say, okay, now is this represented in my complementary? Yes, it's right here, right? So you have to, in fact, multiply by another factor of t. And so it's actually at squared e to the 2t. All right. With with the right-hand side, f of t equals t e to the minus 3t. Well, this is, let's go back up to the chart. We have something like this. You'll notice that this is a degree 1t in the problem below. So we're going to have a degree 1 polynomial in parentheses times e to the minus 3t. So we're going to have at plus b e to the minus 3t. And now you ask, okay, is this represented in my complementary? Well, this is an e to the minus 3t, so no. All right, so this one is definitely the hardest for number 11 here. So let's see what we can do. I'm going to leave a little bit of space, but we see it's very similar, right? We have a degree 2 polynomial times e to the 2t. So that means that our guess is going to be the same. But now, check if any of this is represented in your complementary. So you'll notice that if you were to expand all of this out, you would get a constant times e to the 2t, right? Well, that's already represented in your complementary. So what do? You hit all of this with a factor of t. Okay. Now, in your mind, expand all of this out. What you would get is a ct, a c times t, e to the 2t. So a constant times a constant times t times e to the 2t. Is that represented in your complementary? Yes, it's actually right here, right? So one factor of t was not enough. We actually need 2. And now if you expand everything out, this the worst you'll do is c times t squared e to the 2t. The rest of these are higher powers of t. And none of those are represented in our complementary. So now we are done, right? So this is what your form of yp would look like. So you start with what the chart tells you, and then just go back and double check that you're not reusing anything from yc. I hope that's starting to click as we go through these. Okay, now coming down here, I encourage you to pause the video and try these on your own, but we're just gonna go ahead and power on through. So first we'll solve the complementary by finding the characteristic equation. All right, so we get a double root of 5, which says yc is c1 e to the 5t plus c2t e to the 5t. All right, so coming over here, well, this is a degree 2 polynomial, so yp should just be a degree 2 polynomial. That's our initial guess. Is any of this represented in our complementary? No, right? These all have e to the 5t's, none of these do, so we're good. We come down here. We have an e to the alpha t cos beta t, right? So if you go back and look at the chart, I'm not going to, that's too much scrolling. What you'll see is that you're going to need an a e to the 5t cos 5t plus b e to the 5t sine 5t. And once again, you know, compare with yc, is anything being reused? Well, we do have e to the 5t's, but these don't have sines and cosines, whereas these do, right? So nothing is being reused, and I think we're all good. Here we have e to the minus 2t, so I think we just need a constant times e to the minus 2t, and you go over here, is anything being reused? No, these are all e to the 5t's, so we're done with that one. Now here, this one says we're going to need a constant times e to the 5t, but, okay, I've left some space, so hopefully you see what's coming. A constant times e to the 5t is right here. Power of t is not enough because there's a constant times t e to the 5t, so I need a factor of t squared, right? And then finally, we get yp equals, well, I'll leave a little bit of room. I think you can probably see why. But we have a degree 1 factor of t times e to the 5t, so we're going to need a linear polynomial times e to the 5t. And now check. Well, this is technically a constant times e to the 5t. That's already represented right there. So I need at least one factor of t. Well, check again. Now you have an at squared e to the 5t, which is not over here, so we're good. But we have a b times t e to the 5t, which is right here, right? Constant times t times e to the 5t. And so we need another factor of t. And now there's no duplicates, right? If we expand this all out, we get a bt squared e to the 5t, that's not here. And we get an at cubed e to the 5t, that's also not here, right? So we need another factor. We needed a factor of t squared to get this done. All right, well, that's it for this page. And for the Unit 3.2 notes in general, hopefully this helps you get a good start on the